Determine whether or not the vector field is conservative using curl. If it is conservative, find the potential function. Okay, so here we have a vector field with components x, e to the negative x, negative e to the negative x, and z. And we want to find a potential function if it's conservative. But maybe it's not conservative, so we'd be wasting our time if we started integrating the individual components, right? And differentiating. So we have one theorem from 16.5 that says if the curl is equal to 0, the curl of the vector field is equal to 0, then yeah, there is a potential function. In other words, the vector field is conservative. So that means there is a potential function. So let's take the curl and see if it's equal to 0. So, okay, the curl, how do we remember this? Everybody watch that video? The curl of f, so we're supposed to have a quiz on that video today, actually. Del cross f is the way we remember it, right? And so this is where it starts getting kind of weird because del isn't a real vector, right? We made a vector out of notation, out of operations, but it works. So how do we set this up? Okay, I, j, k, and then across the middle, d dx, d dy, d dz, and then the bottom row would be the entries from the vector field, x e to the negative x, minus e to the negative x, and z. Now, it's not a true cross product, right? Because instead of actually multiplying, we're taking derivatives, but it looks the same, and so we use this as a mnemonic device, right? So, okay, cross out first column, and really what you do to get your entry, your first entry in the curl is a vector field, right? We think of it as a type of derivative, but it's a vector derivative as opposed to the divergence, which is a scalar derivative of a vector. So we take the derivative of z with respect to y. What's that? Derivative of z with respect to y, d dy of z, same as dz dy. Isn't that 0? Minus what? d dz of negative e to the negative x. Isn't that 0? Yes. So 0 minus 0 for the first component. So that's 0. So far, so good. By definition, there's a minus there. Okay. Let's cross out the middle column, and then cross it, but it's not multiplication, it's taking derivatives. d dx of z, 0 again. d dz of x e to the negative x, 0. So minus 0, so the j component's 0, plus, okay, cross out that guy, d dx, something non-zero. d dx of negative e to the negative x, what's that going to be? So positive e to the negative x, when we go that way, d dx, yeah. And then d dy, so what do we get? Minus 0. Times k. So what is that telling you? So you get e to the negative x times k, or if you prefer component form, 0, 0, e to the negative x. So does this equal the 0 vector? All right. So not equal to the 0 vector, so f is not conservative. So we're going to bother trying to find a potential function? No, you stop there. So what is that like that you're used to? That's like when you try to integrate something like e to the x squared. You might have been told or shown in Calc 2, there is no closed formula for that, right? I mean, I guess you could use a Maclaurin series for it, but there is no way in closed form, in non-series form, to integrate that. So there is no antiderivative, right? So the analogy here is the the potential function would be like your antiderivative. There's no antiderivative for this vector field f. There's no potential function for this vector field f. It means the fundamental theorem of line integrals, one thing it means is that does not apply. So when you integrate over a path with respect to the vector field, it's not path independent.